will not believe what I am going to say. It was a night before an exam, physics exam. There's lot of things I have to cover. So I got an idea. Why can't I call the greatest scientist lived on earth to teach me the physics? And I brought him using the time machine. But actually, what has happened is totally unimaginable.
Intriguing. Who dares disturb my eternal experiments? And what is this strange world of yours?
Finally, I brought you back to future. I need your help. I am a student struggling with physics. Can you teach me?
Physics? My dear friend, physics has evolved tremendously since my time. Relativity, quantum mechanics, even my own ideas have transformed.
That's fine. Just teach me what you know.
But tell me, what do I get in return?
If you teach me physics, I would teach you chemistry.
Chemistry? Ha! What's so special about chemistry?
What not so special about chemistry? Everything is chemistry. Everything around us is made of chemistry. Even the air we breathe isn't a pure substance. It's a mixture of gases like oxygen, nitrogen, and carbon dioxide. In fact, in normal life, we rarely come across pure substance. Almost everything is a mixture of two or more pure substance. Their utility depends on their composition. For example, brass, German silver, bronze are made up of similar kind of metals. But each has different properties. In another case, 1 part per million of fluoride in water prevents tooth decay, but 1.5 parts per million can cause tooth molting. At high concentration, fluoride can even be poisonous. It is used in rat poisons.
Fascinating. I had underestimated chemistry. Maybe there's more to it than I thought.
And that's just the beginning. Let's start with solution, one of the most important concepts in chemistry. A solutions are homogeneous mixture of two or more than two components where the composition is uniform throughout. Solutions can exist in different states like gases, liquid, and solid.
Tell me, how do chemists measure how much of one substance is mixed into another?
That's where concentration comes in. There are several ways to express concentration depending on what we need to measure. Let's break them one by one. First is mass percentage. Mass percentage tells us how many grams of substance, that is solute, are present in every 100 gram of the entire solution. The formula for mass percentage is mass percentage of a component is equal to mass of the component in the solution divided by total mass of the solution into 100. For example, if a bleaching solution has 3.62% of sodium hypochlorite, that means in 100 gram of the solution, there are 3.62 grams of sodium hypochlorite. This is especially used in industries where chemicals are mixed by weight. Next one is volume percentage. Volume percentage is used when both the solute and the solvents are liquid. It tells us how many milliliters of solute are present in 100 milliliters of solution. The formula for volume percentage of a component is equal to volume of the component divided by total volume of the solution into 100. Take 10% of ethanol solution. Here 10 milliliter of ethanol is mixed with enough water to make a total volume of 100 milliliter. This measure is common in beverages, perfumes, and medical solutions. Next is mass by volume percentage. Mass by volume is often used in medicine. It expresses the concentration as the number of grams of solute per 100 milliliter of solution. For example, a 5% of glucose dip means that there are 5 grams of glucose in every 100 milliliter of solution. This method ensures precise dosages in medical applications. Next one is parts per million. Parts per million or ppm is used for very small concentration. almost like a pinch of something in a huge amount. Parts per million is calculated by number of parts of the component divided by total number of parts of all the component of the solution into 10 power 6. For example, if drinking water has 1 ppm of fluoride, that means there are 1 gram of fluoride in 1 milligram of water. Even such a tiny amount can be beneficial as 1 parts per million help prevent tooth decay. But too much could be harmful. Next one is mole fraction. Mole fraction is the ratio that compares the number of moles of one component to the total number of moles in the solution. If Na is the number of moles of A and Nb is the number of moles of B, we can find mole fraction of A by Na divided by Na plus B. For example, if you mix 2 moles of ethanol with 8 moles of water, the mole fraction of ethanol is 2 divided by 2 plus 8, which equals to 0.2. This unit is especially useful when working with gases, gas mixtures or calculating vapor pressures. Now we are moving into molarity and molality. Many people confuse here. Formula for molality is equal to moles of solute divided by volume of solution in liter. Molarity tells us how many moles of solute are present in 1 liter of solution. For example, if you dissolve 5 gram of sodium hydroxide in 450 milliliter of water, you first calculate the moles of sodium hydroxide, that is 5 gram divided by 40 gram is equal to 0.278 molality. This unit is widely used in laboratory. Next is molality. Molality is the number of moles of solute per kilogram of solvent. For instance, if you dissolve 1 mole of potassium chloride in 1 kilogram of water, the molality is 1. The advantage is that molality doesn't change with temperature since mass remains constant, unlike volume which can expand or contract. This makes molality ideal for experiment involving temperature changes. Formula for molality is equal to moles of solute divided by mass of solvent in kg.
So I have a doubt. Have you ever mixed sugar in water? It disappears, right? But if you try mixing sand, it won't dissolve. Why does this happen?
This is because of solubility. Solubility of a substance is its maximum amount that can be dissolved in a specific amount of solvent at a specific temperature. Solubility usually depends on 3 things: the type of substance, temperature and pressure. Not all substances dissolve in every solvent. We follow the like dissolve like rule. Polar solutes dissolve in polar solvents while non-polar solutes dissolve in non-polar solvents. Temperature plays a huge role in solubility. When solubility increases with heat, the process is endothermic. When solubility decreases with heat, the process is exothermic. For example, sugar dissolves better in hot tea because its dissolution is endothermic. Pressure affects gases more than solids in liquid. According to Henry's law, as pressure increases, more gas dissolves in a liquid. For example, when you open a carbonated drinks like Pepsi or Coca-Cola, you can see carbon dioxide escaping. Compare this to a simple water bottle. If you blow carbon dioxide from your breath into the water, you will notice the difference. This demonstrates how pressure affects gas solubility.
What is Henry's law?
Henry's law states that the amount of gas dissolved in a liquid is directly proportional to the pressure of the gas above the liquid, provided the temperature remains constant. Now let me tell another one example. For scuba divers, solubility is a matter of life and death. At deep levels, nitrogen dissolves in their blood due to high pressure. If they rise too fast, the nitrogen forms dangerous bubbles, leading to decompression sickness. So they must ascend slowly and make decompression stop at specific depths. Some divers also add helium to their breathing mixture.
Actually, aren't they breathing oxygen? Then why do they need to add nitrogen to their tanks?
Scuba divers don't breathe pure oxygen because it can be dangerous at high pressure. It may cause oxygen toxicity.
Then why don't they fill the tank with helium and oxygen?
Nitrogen is far more abundant in atmosphere compared to helium. This widespread availability makes nitrogen the practical choice for filling scuba tanks.
Wow! Is there anything else we should know about solubility?
Yes, now let me tell about vapor pressure. When a solution is kept in closed container, some liquid molecules evaporate into vapor. Over time, the rate of evaporation balances with condensation, forming an equilibrium where the vapor pressure remains constant. French chemist Francis Rolt discovered that in a solution of two volatile liquids, the vapor pressure of each component depends on its mole fraction. This is called Raoult's law. Mathematically, if the partial vapor pressure of component 1 is equal to P1 dot into x1 and partial vapor pressure of component 2 is equal to P2 dot into x2, then the total vapor pressure is equal to P1 plus P2. The total vapor pressure depends on the composition of the solution. If a more volatile liquid, that is with high vapor pressure, is added, the pressure increases. If less volatile liquid is added, the total pressure decreases. In the vapor phase, the composition of gases is determined by Dalton's law of partial pressure, which states that the pressure exerted by each gas is proportional to its mole fraction in vapor phase. Its formula include P1 is equal to Y1 into P total and P2 is equal to Y2 into P total.
What is volatile liquids?
A volatile liquid is one that readily vaporizes or easily converts into vapor at normal temperature and pressure. When kept in open container, a volatile liquid will evaporate and vapor will disperse into the surrounding atmosphere. Examples of volatile liquid include liquefied petroleum gas, petrol, alcohol, mercury, and gasoline.
Now what happens when we add a non-volatile solute, like salt or sugar, to the liquid?
The solute particles occupy space of the surface, leaving few solvent molecules available to evaporate. As a result, the vapor pressure decreases.
So what is the use of studying this?
Have you ever wondered how pickles, jam and salted meats last so long without spoiling? The answer lies in vapor pressure and osmosis. When salt or sugar is added to the food, it dissolves in water, reducing the vapor pressure. This means there is less available water for bacteria and mold to grow, preventing spoilage. Refrigerants like ammonia work by evaporating at low vapor pressure, absorbing heat and keeping things cool. Things will get more interesting now. Have you ever mixed two liquids together and noticed something strange? Maybe they mix perfectly or they behave unpredictably, evaporating faster or even refusing to separate. Why does this happen? Imagine two liquids, let's say hexane and heptane. When we mix them together, nothing unusual happens. The forces between their molecules remain almost the same as before. This is what we call an ideal solution, a solution that follows Raoult's law perfectly. Key features of an ideal solution include no heat is absorbed or released during mixture, no expansion or contraction in volume. The vapor pressure of each component follows Raoult's law exactly. But most real-life solutions are not ideal. They show a deviation from Raoult's law, meaning their molecules either attract too much or too little. This brings us to non-ideal solutions. Imagine you are mixing ethanol to acetone. Ethanol molecules normally stick together through hydrogen bonding, but when acetone is added, it disrupts the bond. Now ethanol molecules escape more easily, increasing vapor pressure. This is called positive deviation from Raoult's law. Key signs of positive deviation are weaker intermolecular forces between different molecules, high vapor pressure than the expected, more evaporation than in pure liquids. Now let's take a different example, chloroform and acetone. This time, instead of weakening interaction, they form stronger bonds. Chloroform molecules create hydrogen bonds with acetone, making it harder for molecules to escape. This results in lower vapor pressure than expected. This is called negative deviation from Raoult's law. Key signs of negative deviation includes stronger intermolecular forces between different molecules, lower vapor pressure than expected, less evaporation than in pure liquids. Some liquid mixtures boil at fixed temperature and can't be separated easily. These are called as azeotrophs. Azeotrophs are divided into two types, minimum boiling azeotrophs and maximum boiling azeotrophs. Minimum boiling azeotrophs boils easily because it is hard to separate their bonding, while maximum boiling azeotrophs boils with difficulty. Example of minimum boiling azeotroph is ethanol plus water at 95% is used in alcoholic beverages and fuels. Example of maximum boiling azeotrope is nitric acid and water is used in industries. Now let's see a fascinating concept called colligative properties. These properties depend only on the number of solute particles in a solution, not their identity. Let's explore them one by one. The first colligative property is lowering of vapor pressure. When a non-volatile solute is added to a solvent, it reduces the number of solvent molecules at the surface. This means fewer molecules escape as a vapor, leading to lower vapor pressure. This is why salt water evaporates more slowly than pure water. Next up, boiling point elevation. Since the vapor pressure is reduced, more heat is required to make the solvent boil. The boiling point of solution increases. On the flip side, we have freezing point depression. The solute particle disrupt the formation of a solid crystalline structure, lowering the freezing point. That's why salt is used to melt ice on roads in winter. Finally, let's talk about osmotic pressure. The pressure required to stop solvent molecules from moving through a semi-permeable membrane. This principle is crucial in biological processes, like how plants' roots absorb water.
From the chemistry, I know I got a doubt. Dissolving 1 mole of potassium chloride, KCl, in water should theoretically yield 1 mole of K ions and 1 mole of Cl ions. That means 2 moles of particles are released into the solution. Now, if we ignore enterionic attractions, adding 1 mole of KCl to 1 kilogram of water should increase the boiling point by 1.04 K. But what if we didn't account for the degree of dissociation?
We might incorrectly assume that the 2 moles of particle came from a single 74.5 gram of potassium chloride, leading to the false conclusion that molar mass of potassium chloride is 37.25 gram per mole instead of its actual value. This discrepancy highlights an important rule. When a solute dissociates into ions, the experimentally determined molar mass is lower than the true value. On the other hand, molecular association increases the molar mass. Take cetanoic acid in benzene as an example. Due to hydrogen bonding, acetic acid molecules form dimers, reducing the number of particles in solution. If complete dimerization occurs, the boiling point elevation or freezing point depression will be half of its expected value. As a result, experimentally calculated molar mass will be double of its actual value. This phenomena is known as abnormal molar mass. To account for such deviation, Jacobus Henricus van Hoff introduced the van Hoff's factor in 1880. Here, I is equal to normal molar mass divided by abnormal molar mass, or I is equal to observed colligative property divided by calculated colligative property. For dissociation, I is greater than 1. For association, I is less than 1. For example, aqueous potassium chloride solution has an I value close to 2 because it fully dissociates. Acetic acid in benzene has an I value close to 0.5 due to dimerization. The Van Hoff factor modifies colligative property equation. Relative lowering of vapor pressure of solvent is now turned into I into N2 divided by N1. Elevation of boiling point is, that is delta Tb is equal to I into Kb into M. Depression of freezing point delta Tf is equal to I into Kf into M. Osmotic pressure of solution is equal to I into N2 RT divided by V.
I think I am saturated with chemistry knowledge. But I have a doubt if you could bring me here using time machine and explain chemistry so well. What doubt do you have in physics?
Actually, I brought you here to make a YouTube video named Tesla Teaching Me Physics. But it ended as I taught chemistry to Tesla. See the camera there.